Right now, beneath a dying lake in Southern California, a fault no one knew existed is rewriting everything scientists thought about the next great earthquake. The San Andreas Fault has not produced a major rupture on its southern end in over 300 years. That silence was already terrifying, but in 2016, researchers discovered a second fault running parallel to it, hidden beneath the Salton Sea, and the implications sent shockwaves through the seismology community. Why did one of the most studied earthquake zones on Earth conceal an entire fault line? What has this hidden fracture been doing to the stress building along the San Andreas? And if the southern segment finally snaps, could the Salton Trough Fault be the trigger that sets it off? The San Andreas Fault stretches roughly 1,200 kilometers through California. It marks the grinding boundary between the Pacific and North American plates. The southern segment, running from Parkfield down to the Salton Sea near Bombay Beach, is capable of unleashing an earthquake of magnitude 7.8 or greater, according to USGS rupture scenarios. Some models suggest the southern segment alone could produce a magnitude exceeding 8.0. The USGS considers the southern San Andreas the most likely fault in California to host a large earthquake, with the state's overall probability of a magnitude 7.5 or greater event in Southern California estimated at 37% over the next 30 years. But the story is not that simple. The southern end of the San Andreas does not behave like a single clean fracture. Southeast of Los Angeles and northeast of San Diego, beneath the vast Salton Trough Basin, the fault system splinters into a maze of structures. For decades, scientists mapped the major strands and believed they understood the network. They were wrong. A fault lay hidden in plain sight, submerged under shallow, salty water and buried beneath thousands of years of sediment. What came next changed everything. Scientists from the Scripps Institution of Oceanography and the Nevada Seismological Laboratory named it the Salton Trough Fault. It runs parallel to the San Andreas, positioned along the eastern edge of the Salton Sea. This is not a minor crack in a remote desert. It sits dangerously close to the most critical and most overdue segment of the San Andreas system, the segment seismologists have warned about for decades. The Salton Sea region is not a simple single fault zone. It is a web of intersecting fractures, hidden beneath soft sediment and obscured by the lake's murky water. The discovery of the Salton Trough Fault forced researchers to confront an uncomfortable truth. Their hazard models, their ground-shaking predictions, their rupture scenarios for the so-called Big One may have been built on incomplete information. And the fault had been hiding for a reason. Two factors conspired to keep the Salton Trough Fault invisible. First, it lies submerged beneath the Salton Sea, blanketed by complex layers of sediment deposited over millennia. Imaging a fault through that kind of cover is extraordinarily difficult. Standard surface mapping techniques simply could not reach it. Second, and more unsettling, the fault was seismically quiet. Most active faults betray themselves through a steady trickle of small earthquakes. Seismometers pick up these microtremors and use them to trace the fault's path underground. The Salton Trough Fault produced almost none. It sat in silence, accumulating strain without a whisper. This is not without precedent. The Cascadia subduction zone, stretching from Northern California to British Columbia, remained unrecognized as a major seismic threat for decades precisely because it was too quiet. The absence of small earthquakes does not mean safety. Sometimes it means the opposite. It means the fault is locked, building pressure, waiting. But the ground had one more secret. In late September 2016, over 200 small earthquakes rattled the Salton Sea area in roughly 24 hours. The swarm included multiple events above magnitude 4.0, centered near Bombay Beach, just a few miles from the southern tip of the San Andreas. It was one of only a handful of comparable swarms recorded in the region since the early 1930s, following notable clusters in 2001 and 2009. The USGS issued a rare advisory, warning that the probability of a magnitude 7 or greater earthquake on the southern San Andreas was temporarily elevated. During similar swarms in later years, the agency would calculate odds as high as 1 in 100 over the following week, compared to a normal baseline of roughly 1 in 10,000. The 2016 swarm did not trigger the big one, but it illuminated something far more consequential. At nearly the same time, the Scripps team published their findings in the Bulletin of the Seismological Society of America, revealing the Salton Trough Fault for the first time. The coincidence of timing was striking. The research had been underway for years before the swarm, but the publication landed just as the ground was shaking, lending the findings immediate urgency. No one saw it coming. To map a fault hidden beneath a shallow, sediment-choked lake, scientists had to abandon conventional methods. The Scripps and Nevada team deployed an arsenal of instruments rarely combined in a single study. Multi-channel seismic data allowed them to peer through the layered mud beneath the Salton Sea. Ocean bottom seismometers, placed directly on the lakebed, recorded vibrations too faint for surface stations to detect. They also used LiDAR, light detection and ranging, to map deformation patterns in the sediment layers surrounding the sea. Together, these tools revealed a strike-slip fault hidden within the lake, running west of and parallel to the San Andreas. The deformation patterns were unmistakable. Sediment layers were offset and warped in ways that only sustained tectonic movement could explain. The difficulty of imaging this fault cannot be overstated. Without the swarm activity to guide their instruments, and without the combination of marine and terrestrial technology, the Salton Trough Fault might still be invisible today. And the basin itself was designed to hide evidence. The Salton Sea is not a normal lake. It sits within the Salton Trough, a vast pull-apart basin created by the same tectonic forces that drive the San Andreas system. The trough is the northernmost extension of the Gulf of California rift, a place where the Earth's crust is being actively torn apart. In some areas, sediment deposits reach over 6,000 meters deep. For more than 3,000 years, the Colorado River periodically diverted from its course to the Gulf of California and flooded northward into this basin, creating an ancient body of water known as Lake Cahuilla. The lake filled and dried repeatedly as the river shifted, leaving behind thick, complex layers of fine sediment, exactly the kind of material that buries and conceals fault traces. The modern Salton Sea was born in 1905 when floodwaters breached an irrigation canal and the Colorado River poured uncontrolled into the basin for nearly 2 years. By the time the Southern Pacific Railroad finally sealed the breach in 1907, the lake had expanded to become California's largest body of water. Over the following decades, agricultural runoff sustained it, though the lake has been shrinking steadily in recent years. The basin accumulated layer upon layer of sediment, building a perfect geological archive and a perfect cover for whatever lay beneath. The evidence was always there, buried under mud and time. Here is where the story takes its most unsettling turn. Discovering a new fault running parallel to the San Andreas does not automatically mean more earthquakes are coming. The more disturbing possibility is the opposite. The Salton Trough Fault may help explain why the region has had fewer large earthquakes than expected. Paleoseismic studies have shown that the southern San Andreas has produced magnitude 7 earthquakes roughly every 175 to 200 years for the last 1,000 years. Yet no major rupture has occurred on this segment for over 3 centuries, breaking the expected rhythm. The seismological community has struggled to explain this prolonged silence. The Scripps team offered a hypothesis. Based on the deformation patterns they observed, the Salton Trough Fault appears to have been accommodating some of the strain from the larger San Andreas system. This could imply that instead of all the tectonic stress concentrating on a single fault, it has been quietly distributed across multiple structures beneath the Salton Sea. If that interpretation is correct, the fault may have been acting as a kind of pressure valve, something that, based on what we know, could help explain the anomalous silence. This is not reassurance, it is a deeper kind of uncertainty. If the Salton Trough Fault has indeed been absorbing strain, then the stress budget of the entire southern San Andreas network would be more complex and less predictable than anyone modeled. The question would no longer be just when the San Andreas will rupture, it would be what happens when both faults interact, whether simultaneously, sequentially, or in some pattern science has not yet imagined. And that is precisely what no one can answer. The central uncertainty is blunt. There is no clear record of past earthquakes on the Salton Trough Fault itself. Scientists do not yet know how often it ruptures, how large its earthquakes can be, or whether it interacts with the San Andreas at depth. The Nevada state seismologist who co-authored the discovery put it plainly: without a record of past earthquakes from this new fault, determining its relationship to the San Andreas is extraordinarily difficult. Is the strain being absorbed, shared, transferred, or is it quietly building toward a separate rupture that no hazard model accounts for? Each scenario carries different consequences for millions of people, and the data to distinguish between them does not yet exist. What we can infer from the deformation patterns is that some interaction is occurring, but mapping faults is far easier than predicting how they communicate underground. That uncomfortable truth sits at the heart of this story. The silence beneath the Salton Sea may be the most dangerous signal of all.
This is why the USGS launched its most comprehensive investigation of faults beneath the Salton Sea. Led by research geophysicist Ganny Brothers, the effort used sonar surveying and sediment coring to characterize the full network of faults hidden under the lake. Before anyone can do the engineering work required for these restoration projects, they have to know where active faults are located, their history of movement, what the geotechnical properties are of the sediment they're building on, Brothers explained. The northern and central portions of the San Andreas have relatively well-established seismic histories, built from decades of paleoseismic trenching. The southern end, submerged beneath the Salton Sea, had resisted similar study until now. The team identified as many as 14 ancient Lake Cahuilla sediment sequences preserved in the lakebed, spanning roughly 3,000 years. Within these layers, they found offset strata, disrupted sequences, and growth patterns across fault zones, the fingerprints of past earthquakes written in mud. At least 4 of these displacement events may have coincided with major ruptures along the southern San Andreas, a probability that returns to background levels only after the swarm subsides. But the pattern appears to be intensifying. USGS probability estimates during active swarms have placed the chance of a magnitude 7 or greater event as high as 1 in 100 over the following week. In a typical week, those odds sit at roughly 1 in 1,500. Each swarm is a roll of the dice, and with the discovery of the Salton Trough Fault, the number of variables in the equation just increased.
The immediate questions remain unanswered. If the San Andreas ruptures, what does the Salton Trough Fault do? Does it rupture independently? Does it follow in sequence? Does it transfer stress deeper into the system? Or does it absorb energy and delay the cascade? No existing model accounts for all possibilities. The ground keeps speaking, and scientists keep listening. Most people picture the San Andreas as a single zipper running through California. That image is wrong. At its southern end, the fault dissolves into a labyrinth of structures beneath the Salton Sea. The San Andreas, the San Jacinto, the Imperial, the Brawley Seismic Zone, and now the Salton Trough Fault all converge in this region, creating one of the most complex tectonic junctions on the planet. Seismic activity around the Salton Sea could potentially trigger larger earthquakes along the San Andreas system, according to USGS assessments. The stress does not simply sit in one place. Based on what we know about fault mechanics, it migrates, transfers, and accumulates across faults that may be connected at depth, even when they appear separate on the surface. The the central question has become, where is the stress going? Is it stored in the locked southern San Andreas, redistributed into the web of faults beneath the Salton Sea, quietly shared over geological time, or building toward an unrecognized future rupture on a fault we only just found? And there is one more dimension of risk that scientists are only beginning to grasp. A 2025 study published in Geosphere by Oregon State University's Chris Goldfinger found evidence that the Cascadia subduction zone and the northern San Andreas fault may be partially synchronized, with earthquakes on one system potentially triggering the other. Some seismologists have cautioned that the evidence, based on sediment core dating, carries significant uncertainty, but if even a partial link exists between fault systems at both ends of the San Andreas, the idea of a single isolated big one could itself be outdated. The lakebed hides the receipts. The only dataset for the future is the past, locked in sediment cores and offset strata beneath a shrinking, toxic lake in the desert. Scientists know the Salton Trough Fault exists. They know the evidence suggests it has been absorbing strain. They know the southern San Andreas is centuries overdue. They know that swarms keep coming and that each one raises the odds. What they do not know is whether the next swarm will be the one that finally tips the balance, or whether a fault discovered less than a decade ago holds the key to a rupture scenario no one has yet modeled. The ground beneath the Salton Sea is not quiet, it is waiting, and the question that no scientist can yet answer is the only one that matters. When it finally moves, how far will the shaking reach?